Okay, so yeah, we were discussing about the orthogonal complement, right? So the initial starting point is the given subspace W, and W is spanned by some linearly independent vectors, right? And then the orthogonal complement to this the given subspace is set of all the vectors that are orthogonal or perpendicular to any vector from initial subspace W. And yeah, there are infinitely many possibilities because our subspace W will contain infinitely many different vectors, but they are anyway spanned by a finite number of basis vectors. For example, if W is spanned by these two vectors, and then our W perpendicular or orthogonal complement to this subspace is, contains the vector that is orthogonal to only those basis vector of our subspace. And then it leads us to the fact that this vector orthogonal to these two bases is also orthogonal to any vector which is a linear combination of these two vectors, right? And then we also briefly discussed about why we call it as orthogonal complement. So complement is in Korean, it's like 이제 여집합이라고 얘기했죠. Okay, so as a important property, of W perpendicular, this W perpendicular is also a subspace, okay, spanned by a finite number of linearly independent basis vectors, right? And then if W is spanned by 4 linearly independent vectors, maybe out of R5, and then the dimension of W is 4, and then W perpendicular or orthogonal complement to this W is spanned by a single or only one linearly independent basis vectors, right? And if it is 3, then it will be 2. And so the sum of these dimensionality of these two subspace W and W perpendicular will always sum up to the entire the dimension of the entire vector space, which is 5. Okay, and then let's relate or let's study how this orthogonal complement is related to a given matrix. Okay, so let's think of this matrix A. Okay, and then what is the column space? It's of course spanned by 1, 2, 3, and 2, 3, 4, right? Okay, and then now we know, we understand the meaning of the perpendicular or the particular subspace perpendicular. So this is subspace, right? And then what about its perpendicular? Okay, so in this case we know that this set of vectors is containing those vectors that are orthogonal to those two vectors, right? And in order to rewrite this relationship in another way, so let me show a simple trick. So let's consider A transpose. So A transpose is now including the rows as the columns of A, right? So previously our columns has now become rows in A transpose, so it's obvious, right? And then what about the null space of A transpose? So we studied about the null space. It's simply the set of all vectors that satisfies this solution, and A transpose is this guy, right? So 1, 2, 3, and 2, 3, 4. And first of all, what's the dimension of an x? X is three-dimensional vector, right? x1, x2, x3, and that should be all 0, right? And in this equation, yeah, we previously studied about the parametric vector form, right? In order to represent the general kind of solution, and also the basis of this null space, right? So we perform this Gaussian elimination and so on, right? But now we apply a slightly different perspective, which is also quite simple. So here, let's consider some inner product perspective. So it should be, yeah, because we are discussing or studying the inner product. So we can think of the inner product between 1 to 3, and x1, x2, x3 should be 0. And what does that mean? This x1, x2, x3, this vector is perpendicular or orthogonal to 1, 2, 3, right? So the first equation in this homogeneous linear system is x is perpendicular to 1, 2, 3, right? And then what about the second condition, or the second equation? So these two inner product should also be 0, right? So these two conditions or requirement is exactly the same requirement to form our W perpendicular, right? And what is our original W? W is span of these two, right? So suddenly, the perpendicular, the column space of a perpendicular, okay? So orthogonal complement of this column space of an A is equal to the null space of A transpose. Does it make sense? Because by definition, yeah, we have to omit, oops. By definition, the null space of an A transpose contains the rows as the columns of an A, right? And then it works as like this part where we have like A1 transpose. So let's call this guy as A1 as a first column and A2 as a second column, and A1 transpose X should be 0, A2 transpose X should be 0, right? So we need the rows, right? And in order to obtain the rows, we just formed A transpose, and the null space of an A transpose, or the solution of our homogeneous linear system of A transpose X is equal to 0. So that is orthogonal complement of this column space of an A. Okay? Right, and then let's consider the dimensionality of the column space of an A. So what's the dimension of it? So it is spanned by the two linearly independent vectors, right? So the dimension of the column space of an A is 2, right? And then what about the null space of an A transpose? So purely looking at this homogeneous linear system, yeah, let's imagine performing this Gaussian elimination and then extract out some this vector, yeah, parametric vector form. Okay, so we will just factor out the free variable and then obtain a particular constant vector, right? And then how many basis vectors will we obtain from this homogeneous linear system? And that will be the number of free variables that we have, right? So here, so we have 3 columns in 2-dimensional space, right? So what's the dimensionality of the null space? So the first one is linearly independent. Second one is linearly independent. So the third one should be linearly dependent one. So we have a one free variable, and so the dimensionality of the null space will be 1, right? Okay, so this guy, the dimensionality will be 1. And again, yeah, so when when obtaining the parametric vector form of this null space solution, we will consider like two-dimensional vectors. But what is the dimensionality of our null space solution? It is still living in the three-dimensional vector space, right? So here, the column space of an A basically contains the three-dimensional vectors like 1, 2, 3 and the 2, 3, 4 and their linear combinations, right? And also the null space of A transpose. Okay, so that is basically the three-dimensional vector. So they are living in the same three-dimensional space, right? But their dimensionality, which is the number of linearly independent vectors that will span each of these two subspace, will be 2 and 1, and thus if we add them up, and then we will obtain 3, right? So in that sense, this orthogonal complement, I mean the notion of this the notion of complement is still holding true, right? So again, the point is column space of an A and its orthogonal complement is the null space of an A transpose. Okay, and then now let's consider another case where we have A over here, and so similar to the column space, we can also define the subspace called the row space. Okay, row space. So what will be the definition? So given the matrix A, where 1, 2, 3, 2, 3, 4, and then the row space of an A will be just spanned by the rows of A. So the first one, second one, and the third one, right? And 1, 2, 2, 3, and 3, 4. So this is the row space of an A. So that is the definition. But are these the valid basis of the subspace? It is not, because they are linear. Yeah, they are necessarily linearly independent. Linearly dependent, right? And so we can just pick up or choose the first two linearly independent rows, and then that will be the basis of our row space. Okay, and then now these vectors are living in two-dimensional entire space, right? And then what will be their orthogonal complement? First of all, the dimensionality of row space of an A is what? It's 2. And based on the complementary relationship, what will be the dimensionality of orthogonal complement of row space of an A? It is 0. Should it be 1? Why? So basically, the sum of these two numbers should be the same as 2, right? Because these vectors are basically living in the two-dimensional entire space, right? Okay, and then let's consider this orthogonal complement of row space of an A. Okay, so by definition, the row orthogonal complement of this row space of an A is all the two-dimensional vectors that are satisfying this equation, 1, 2, and 2, 3, right? And we don't need the condition to be orthogonal to 3, 4 because this guy is anyways a linear combination of the previous two, right? So as long as we satisfy these first two conditions, and then this vector x will automatically be orthogonal to 3 and 4 because that is a linear combination of the first two vectors, right? But anyways, we have no problem of writing these additional conditions because they have no effect, right? And these conditions can also be represented as this simple form where we just write A as it is, and then 1, 2, 3, 2, 3, 3, 4, and then x1, x2, which is our two-dimensional vector, and then it will be 0, 0, 0. Okay, so here this guy should be 0, and this guy should be 0, and this guy should be also 0, right? So by definition, Ax is equal to 0, which is a familiar equation that we know as homogeneous linear system, right? So this is basically the orthogonal complement of what? The row space of an A. Okay, so row space of an A perpendicular is what? Null space of A. And again, let's write this guy again. Right? So we have two interesting properties shown here. Okay. And again, given A as 3 by 2 matrix, these guys, row space of an A and null space of an A, are living in R2, right? And these are living in R3, right? Okay, so these are, so from here we have a 4 different subspace: null space of an A, null space of an A transpose, and column space, and the row space. Or this row space of an A can also be written as column space of an A transpose. So this is a quite simple one. So there are these 4 different and also closely related subspace derived from a given matrix A. Okay. So if A is m by n, and then this one will be n, this one will be m, right? So your matrix A and its column space and the null space of an A transpose, they will be complementary to each other, and they will live in the 3-dimensional space, the m-dimensional space, and the row space of an A and the null space of an A, they are both living in n-dimensional space, and they are also complementary. They are the subspaces complementary to each other. Any questions so far? 네. 네, 이거 좋은 질문이네요. So between these two notations, which one is true? The first one. The second one. So you know the meaning, right? You guys know the meaning. So if 1, 2, 3, and 2 is this guy, right? And 1, 3, right? So subspace is basically the subset of the vectors, right? Not just a single vector or single element in this entire set. So it should be this guy, right? So they are basically the subset, or 부분집합이죠, 이게. subspace는 부분 집합인데 리니어리 리니어 컨비네이션에 이제 닫혀 있는 것을 이제 서브스페이스, 그러니까 부분 집합뿐만으로 불리는 게 아니라 부분 공간으로 불리는 거예요. 어쨌건 근데 이제 부분 집합은 부분 집합이죠. 벡터들의 서브셋이니까. Any questions so far? Yes, yeah, these column space and the row space and things like that are a little bit conceptual, and you may have no idea where to use or where it can be useful. But yeah, it is really useful in some applications that we don't discuss much in detail in this class. But yeah, it is an important part to keep in mind. Okay, at least for your exam. Right. So these were a little bit conceptual and a little bit abstract part, but so we covered this, did we? Yeah, probably not. Yeah. Okay, so let me see. So you guys know the inner product between the vectors. So it can give us the angle between the two vectors. So let me see. Okay, so have you studied about this relationship? Did we study in this class? Probably not, right? So let me briefly discuss about it. So the inner product is actually the same as the product of the lengths of each of these two vectors and the cosine theta, where theta is the angle between the two vectors. So let's suppose we want to obtain the cosine theta between these two vectors of 1, 3 and 2, 1, and then we first compute their inner product in this manner. So 5 is our inner product, and separately we obtain or compute their lengths of these two vectors. Okay, and then the square root 5 and the square root 10, and then we can relate this equation as 5 is equal to square root 5 and the square root 10 times cosine theta, and thus cosine theta is this guy. Yeah, 1 over square root 2, right? So in this manner, we can obtain the angle as 45 degrees. So between these two vectors, we can obtain this cosine theta and their corresponding angle from this relationship between the inner product and their lengths and their cosine theta. Okay? Okay, and from this perspective, if theta is 90 degree, and then cosine theta is 0, right? And so even if these two vectors are having a non-zero length, and because this cosine theta is becoming 0, their inner product should be 0, right? And so that way, inner product, if the inner product is 0 and then their angle is 0, their angle is 90 degree, or they are perpendicular to each other, and this relationship can be also proved by the law of cosines, but I will skip this part and let's move to the next chapter of 6.2. Okay, so the next chapter is about orthogonal sets. Okay, so these are related to a set of vectors. So initially we are given a set of vectors. So p number of vectors in R-dimensional space. For example, in R3, suppose we have 1, 2, 3, and 2, 3, 4. Okay, so we are given a set of these two vectors, and so they are, so whether this vector set is orthogonal set or not. Okay, so this is defined based on the following conditions. So we choose any vector, any two vectors from our set, and then they should be perpendicular to each other or orthogonal to each other. Okay, so between these two vectors, if we compute their inner product, then their inner product is not 0, of course, and so they are not perpendicular to each other. So this is not orthogonal set, but they are still linearly independent set, right? So we can now compare between the linearly independent set and also orthogonal set. Okay, and between the two, orthogonal set is much more strict condition. So which means if your set is orthogonal set, okay, and then it is automatically guaranteeing that this set is linearly independent. Okay, but even if the set is linearly independent, it is not orthogonal set, right? As we can see in this example. But interestingly, orthogonal set, okay, is automatically linearly independent set. So that is main important point. So that is about this theorem 4. So intuitively, let's think of the linearly independent set between the two vectors. Okay, so what is the meaning of the two vectors that are linearly dependent? Linearly dependent for the two vectors, and then they will have the same directions, right? And then what about their angle? So in this case, what is the angle? Angle would be 0. Okay, so and then suppose the angle is now just 1 degree. Okay, only small amount of angle of 1 degree, and then this one is linearly independent, right? But it's still far from being orthogonal, right? So being linearly independent can be thought of as having a non-zero angle between the two vectors. Okay, and then what is the maximum possible angles that we can have between the two vectors? That will be having a 90 degree, right? So in this perspective, from this perspective, like orthogonality or orthogonal vectors are kind of maximally linearly independent. Okay? So it is by no means mathematically kind of rigorous or correct kind of statement, but at least from my kind of intuition, I view or I understand the orthogonality as being maximally linearly independent. And what if we have a more than 90 degree angle, like this case? Okay, so in this case, we can consider the angle. So this is 90 degree, and what if our vector has this shape, and then of course the angle will become more than 90 degree, but we can consider also the angle as this guy, which becomes now smaller than the 90 degree, right? So in this sense, 90 degree is the maximum possible angle between the two vectors. Okay. Right, and then what about this case? The first one and the second one, so like this case, so two vectors that are linearly independent, and then now consider the third vector. Okay, the third vector that is also linearly independent. Okay, so in this case, how can we think of this angle? Okay, so in this case of an angle, let's consider this. Yeah, so when checking whether this set of vectors are linearly independent or not, is by adding one vector at a time, and then check whether the current vector is inside of the span of these two vectors, right? And so when considering the third vector, we consider we consider the span of the previous two vectors, right? And then now let's consider the angle between the current vector to add and this plane spanned by these two vectors, okay? And then we consider like right? Yeah. So this is V1 and V2. So we can consider the span of V1 and V2. And what will be the angle between this span and the currently added vector V3. So we can think of like this guy, right? So the angle can be thought of as like a minimum possible angle where we choose any vector from the span, okay, as of course a linear combination of V1 and V2, okay? And then if that vector is like this guy, and then the angle might be 70 degree, and maybe in this direction, and then the angle will be like 60 degree, and so on. But we can consider the vector that makes the smallest possible angle between this plane and this vector V3. And suppose this angle is still maybe 15 degree. Okay, so we scan through any possible vectors, okay, given a fixed V3. Okay, and then we choose the vector that will give us the minimum possible angle. So that angle is still 15 degree. So in this case, so this is a linearly independent, right? Because if we find any vectors and then find out the minimum possible angle, and that angle is still non-zero. But what if the V3 is a linearly dependent one, which means it is included in the span of V1 and V2. So in that case, let's imagine the exact same process, and then what will be the angle? So the minimum possible angle will become 0, right? So in this sense, the angle, if the angle is non-zero, and then it is linearly independent. And if the angle is 0, and then it is linearly dependent. Okay? And then, in the case of orthogonal set, so as I mentioned, this orthogonal set is maximally linearly independent. Okay? So in that case, this angle should be 90 degree. So what should be our vector V3? This guy. So in this case, even if we choose any vector from the span of V1 and V2, so that will be always 90 degree. So that maintains the maximality or the maximum angle, even if we choose any vectors from the span of the previous vectors. Okay, so so in this case, so what is the condition of? So what is the condition of V3 having the maximum possible angle of 90 degree against any vector chosen from the span of V1 and V2? So that is just a V3 is perpendicular to V1 and V3 is perpendicular to V2, right? So if we maintain these two conditions, okay, and then V3 will maintain the maximum degree of like 90 degree, maximum angle of 90 degree with respect to any vector chosen from the span of V1 and V2, because we know the linear combination of V1 and V2 will always be perpendicular or orthogonal to V3, right? Okay, so this is about some intuition about why this linearly or orthogonal set will automatically guarantee the linearly independent set. Okay, but not the other way around. And then let's prove this theorem just kind of mechanically or through some equations. So what is the so we want to prove orthogonal set is automatically linearly independent set. So we want to prove that. Okay. So what is the condition of this linearly independent set? So we have to find there should be only the trivial solution for our homogeneous linear system, right? So suppose we are given U1 through UP, and these vectors are assumed to be orthogonal set, which means any pair of them will be perpendicular to each other, right? And then this is a vector equation form of our homogeneous linear system, right? And then once we can find some non-trivial solution about this C1 through CP, and then that means that these vectors can possibly be linearly dependent, right? And then let's prove that the only possible solution for this is just a trivial solution. Okay, so we want to prove that. And how we prove it is as follows. So in this case, so here there is a one typo over here. So what is the typo? It's a really minor one and subtle one, but this 0, is it scalar or vector? So it's currently, the notation is saying it's a scalar, but C1 and 1, 2, 3, C2 and 2, 3, 4, and it should be vector, right? So it should be vector in the same dimensional space, right? Right? And then now let's apply the inner product. I mean, these two vectors are the same, and so let's apply the inner product with the maybe U1 over here and also U1 over here. Okay, so using the same vector, having two different representations, we applied this the inner product with the same vector U1. Okay, and then the inner product with the 0 vector will remain 0, right? And then this U1 will be just distributed in this manner, and then this guy and this guy, and we can apply associative law. And then what about these parts? So these parts are 0 because of the definition of the orthogonal set, right? And this part will be non-zero, right? Okay, so if this is non-zero, and then we obtain, we conclude that C1 is 0, right? And then likewise, instead of applying or multiplying with the U1, let's compute the inner product with the U2. And then now this term will remain, this one will be the only term that remains, and so the left hand side will still be 0, and so C2 will be 0, right? And so we can easily conclude that C1 through CP, all of them are 0. So we have no possibility, or we have no way to escape from this trivial solution for this homogeneous linear system. Okay, so that way, if the vector U1 through UP are orthogonal to each other or orthogonal set, and then they are automatically linearly independent. Okay, so that is the kind of mechanical proof. Right, and then also let's think of this orthogonal set related to a vector space. The subspace. So let's suppose the subspace W, and then we can consider its basis that fully spans the subspace and that they are linearly independent, right? But we change or replace the condition of being linearly independent with the condition of orthogonal set, okay, which is more strict one, okay. So in that sense, still fully spanning the subspace, and also those vectors are not just linearly independent, but also they are orthogonal to each other. In that case, these vectors are orthogonal basis for the subspace. Okay? So in this case of having orthogonal basis, and then yeah, it makes our lives much easier. Okay? In what sense does it make it easy? So let me show how. So suppose these U1 through UP are orthogonal basis for a subspace W. So again, these are linearly independent, of course. And then our subspace is spanned by these orthogonal basis vectors. Okay, and then suppose we choose a particular point or vector from our W. Okay, so it's like this. Suppose we have the two basis vectors that are perpendicular to each other. Okay, and our subspace is spanned by these two vectors. And then suppose we choose a vector from the subspace. Okay, and then because we chose this vector from the subspace W, and then we should be able to obtain the linear combination representation with respect to this U1 and U2, right? And then now, so let's call this Y, this point as Y from our subspace W, right? And here, yeah, we need this guy over here because Y is a single vector. Right, and then because Y is inside of our subspace, we know Y is represented as a linear combination of these two vectors, of our basis vectors, right? And then let's consider C1 and C2. Okay, so how we can compute it. So so this is an intuitive example. Let's consider the span of these two, which are linearly independent, but they are not yet orthogonal to each other, right? So in this case, let's consider maybe 4. Okay, and then I chose this guy from the subspace W, and let's try to represent it as a linear combination of these two vectors. And in this case, how can we obtain C1 and C2? Yeah. Someone read my mind. Yeah, but yeah, typically, yeah, we will form this linear system, right? And then this one is our B, and this one is AX. So we will have to perform the Gaussian elimination, right? And that's how we obtain C1 and C2, right? And this Gaussian elimination is iterative process, and then yeah, it will involve a lot of steps of performing this Gaussian elimination, right? But what if our basis vectors are initially orthogonal to each other? Okay, so in this case, let's consider this the new W, which is a completely different subspace, and 1, 2, 3, and 2, 3. Right? What will be the minus 1? Sorry. Good. Right? So in this case, yeah, I just manipulated the second vector to be orthogonal to the first one, so that we can obtain the orthogonal basis vector. Okay? So in this case, So you guys read my mind very well, so I have to, okay, I'm going to use the same one. 5, 7, 3. So in this case, still the solution is 2 and 1, but right? C1 and C2, right? So here we almost have the same problem, right? So what we will typically do in order to obtain C1 and C2 will be to obtain or compute the Gaussian elimination by forming the augmented matrix, right? But here, based on these two basis vectors are orthogonal, based on the fact that these two vectors are orthogonal to each other, we can apply some advanced and quite convenient trick that makes our lives much easier. So how we do it is, 뭐 잘못했어요, 피? 네. 네. So here we apply almost the same trick where we used over here to prove this theorem. So let's apply the inner product with the first vector. Okay, so the first vector is inner product. Yeah, I mean it's inner product with the left-hand side. Will be what? 5 plus 7 plus 9, right? And we can easily obtain that. And the point is, 잘못했어요. 3, 3, 9, 7, 24. 네, 얼마죠? 14, 20, 28. Okay, good. Right, and then if we compute the inner product between these two and these two, and then we at least know the inner product between these two will become 0, right? And so here we only have a C1 really conveniently. And now what is the 14? 네. Right? So this is the vector norm of 1, 2, 3, right? Or the inner product with itself of 1, 2, 3, or the first vector, right? And so square, right? Great, great, yeah, great. Okay, so we can easily obtain C1 is 2, right? And so when computing C1, U2 or U3 or and so on, so they are not involved at all. So that's the main beauty of having orthogonal basis for our subspace. Okay? And likewise, we can easily obtain C2 as well, right? And the process of computing C2 will not involve C1 or the U1, U3, and so on, right? So that way, if we have an orthogonal basis vector, and then this, solving this linear system or this linear combination coefficient with respect to orthogonal basis vector is really, really easy. Okay, and it can be computed completely separately. Okay, so in order to obtain C1, we don't need C2, U2 or U3 and so on. We only need U1, right? And our vector Y. Okay, and in order to obtain C2, we only need U2 and no other basis vector as long as they are orthogonal to each other. Okay, right? And then let's generalize this guy. Okay, and then this C1 is represented in this manner, and then it can be written as this guy. So this guy is Y, which was chosen from our subspace, right? And Y and U1, right? So this is this part, right? Divided by what? U1 dot U1, right? So this is C1. And C2, what about C2? This guy, right? So that's how we obtain the linear combination coefficient over here. Okay. Any questions so far? Okay, then let's take a 10-minute break, and then let's resume 1:05 according to that clock. Okay, let's continue. All right. So in this example, yeah, we studied about the convenient ways of obtaining the linear combination coefficient in case we are given a linear orthogonal basis for a given subspace, and when choosing a vector inside of our subspace, and then we can simply obtain their linear combination coefficient in this manner, right? But now let's extend this computation into more general case where this y is not necessarily inside of our subspace. Okay, so in this case, if if y is not inside of our subspace, then we cannot represent it as a linear combination of our basis vector, right? So it's like this. So this is an origin, and this is a u1 and maybe u2, and maybe we have some y over here, okay, which is clearly outside of our span, okay, and then we can think of its orthogonal projection. Okay, so this orthogonal projection is really important part, and we will keep studying it in the later chapters. But yeah, what is the orthogonal projection? So yeah, over here. So let's call this as y hat. Okay, so that is like, yeah, the putting or the landing kind of, yeah, the foot of a perpendicular. Does, yeah, do you guys know the meaning of it? 수선의 발이라 그러죠. 수선의 발. 수선의 발이 진짜 나도 영어로 잘 몰랐는데 또 사전을 좀 찾아봤었는데 진짜 foot of perpendicular인 것 같더라고요. foot of perpendicular. 네, 하여튼 수선의 발. Right? So yeah, we can say this converting y into y hat is called orthogonal projection. So what is the meaning of orthogonal? Orthogonal is determined. So we are initially given the subspace W spanned by U1 and U2, okay? And yeah, so our projection line, okay, projection line should be perpendicular to any vector from any vector in our W, okay? So in this case, so it is perpendicular. So the angle is always like 90 degrees. So you can imagine, yeah, really perpendicular line, yeah, with respect to a flat kind of a plane. Okay. Right. And then given this y, and then we can consider this y hat. And even if y is not necessarily in our W, okay, but y hat is, yeah, we can guarantee that it's yeah, it's inside of our subspace W, right? And then now let's think of the original y as the sum of the projection output, orthogonal projection output, y hat, plus some vector z. Okay, so what is this vector z corresponding to? So z is something like this. So so y hat is over here, so this is y hat, right? So this is the vector of y hat, and this guy is c, right? So if we add these two vectors together, and then we will obtain the original y, right? And what is the angle over here? It is also 90 degrees, right? Okay, so I leave it as it is. Okay, and then here, yeah, let me just give a conclusion. So how can we obtain this y hat, which is orthogonal projection to the subspace W, and W is spanned by some spanned by also orthogonal basis vectors u1 and u2, for example. Okay, so in this case, this y hat is, yeah, you just treat this y as just like the point inside of W, and then you will just obtain the linear combination representation with respect to our orthogonal set. Okay, that is your y hat. Okay, so let me show the example. So over here, yeah, I paid attention to choose the vector in a way that it's the inside of the span of this, right? Span of these two vectors, or the subspace W. But what if, okay, let me bring this example once again. Okay, so we have this subspace W spanned by these two orthogonal basis vectors. Okay, and then I'm gonna give you just an arbitrary vector y as maybe 2, 3, 4. Okay, so in the case of 2, 3, 4, so I just set this vector arbitrarily, and probably this vector is outside of the span of these two vectors. Okay, so yeah, if we just form this 1, 2, 3, 3, 3, negative 3, and 2, 3, 4, and then perform this Gaussian elimination, and then it will probably have the pivot over here, and so it will have no solution at all, right? But still, this guy can be viewed as some points like this, right? And then we can think of its orthogonal projection, right, onto the subspace spanned by these two orthogonal basis vectors, right? And then what will be y hat? Okay, so y hat can be, yeah, y hat is obtained just exactly in the same manner as the previous slide. So this y hat, I mean, I'm just give you the conclusion. So y hat is like y dot u1 and u1 and u1, and so this is u1, right, plus y dot u2 and u2, u2 and u2. Okay, so this is the conclusion that we obtained over here, right, given these two orthogonal basis vectors, right? Right, and then let's just compute it. Again, here the y is clearly the point outside of the span of y, span of subspace W. Okay, but we will just compute this. This same expression anyways. Okay, and then what is the inner product between y and u1? Can anyone give an answer? 얼마죠, 그러면? 20? 20? 20? 2, 3, 6, 4, 32. 요거 두 개. 네, 지금 요거 계산한 거예요. 아, 네. 요거 계산. 네, 분모는 또 계산해야죠. 여기에 14. Okay, so 14. Yeah, so yeah, we should be careful about using the dot product. I mean the notation for this inner product. So this is inner product, right? And this is an inner product, and this is not an inner product. It's just a scalar multiple. So even though this one looks complicated, but this is a scalar, right? Scalar times a vector, right? So in this case, we don't use a dot over here. So it is just a like this. And yeah, just as a side note, u1 dot u is the same as u1 transpose u, right? So in this case, it is a matrix multiplication, right? So it's like 2, 3, 4, 2, 3, 4 is 2, 3, 4, 2, 3, 4 with no dots. So this is 네. 이렇게 자주자주 지적을 해주세요. Right? Okay, so this guy and u1 is 1, 2, 3, and yeah, let's continue. Y dot u2 is 6. This guy, this guy, this guy. Right? 아까 얼마였죠? 아까 안 구했나? u2 3루트 3 339 9317 이렇게 한 거예요. 이거 11 마이너스 1에다가 3배니까 11 마이너스 1의 저기 길이가 루트 3이니까 right? So this times 2, 3, 4 right? Okay, so I'm 여기 얘가 갑자기 왜 튀어나왔다 3 and negative 3 good. Okay, so I'm claiming that this exact same representation as we were using in the case of y being inside of w. Okay, so here y is not inside of w, y is outside of w, and we just wrote this representation anyways. Okay, and then this one will become, yeah, this one is not, yeah, this one is clearly not the same as y because it cannot be equal to y because y is outside of w. But this representation is basically y hat, which is orthogonal projection. Okay? So yeah, that is our conclusion. Although we haven't proved it yet. 네. Right? And then now let's prove this. Okay? So I'm claiming that this is a y hat. Okay? And y is y hat, which is an orthogonal projection part, and plus z. What was z? Z is this guy, right? This guy, right? And z is a perpendicular or orthogonal to our subspace, right? Right, and then, yeah, so let me prove this, and then our y hat is anyways a linear combination of u1 and u2. Is it right? So from here, I just, yeah, without any proofs, I said that, or I claimed that this C1 and C2 can be obtained in this manner, right? But before then, it can be, yeah, it is of course represented as this linear combination of u1 and u2 because once we perform the orthogonal projection and then that projected point y hat is inside of w, right? And then now y minus y hat is our z, okay? So this is this is z, and z is orthogonal to each other, right? And what kind of condition should z satisfy? Z should be orthogonal to u1, and z should be orthogonal to u2, right? Right, and then so here y minus, yeah, so y minus y hat is y minus c1 and u1 minus c2 and u2, right? And u1 is 0 because this is, right? And so once we rewrite it, and 0, right? And so, okay, so C1 is just obtained as the exact same representation as this guy, right? Right, so we proved it, right? We proved C1 and C2, which works as the linear combination for the orthogonal projection point y hat, okay? And then those linear combination coefficients will be obtained in this manner. And yeah, we can also understand this from another perspective. Okay, so here, so basically, in order to represent y, okay, so we have we can consider it as having as a linear combination of the three different vectors. So the first one is with respect to u1 and u2, that will which will form our y hat, right? And then now, we have another kind of component or another basis vector of z, right? And u1 and u2 and z, and suppose c is something like this vector that may not be necessarily having the same length as this c, but we can call that as u3, for example. Okay, so z is formed by y minus y hat. Okay, the difference between the original vector and its orthogonal projection y hat. Okay, but that will form a particular directional vector, and let's consider that direction and another basis vector u3 in this manner, which is parallel to z, and u1, u2, and u3. Okay, so they are still orthogonal set. By definition, u1 and u2 were orthogonal set of a given subspace, and z, by definition of orthogonal projection, this vector z should be orthogonal to any vector from our subspace W, right? And so even if we add this u3 into the previous set of orthogonal vectors, and altogether these sets will be still orthogonal vectors. Okay, and then now let's imagine representing y as the linear combination of u1, u2, and u3. Okay, and then how can we compute their linear combination coefficient? By the fact that these three vectors are linear orthogonal to each other, we can obtain the linear combination coefficient completely separately, one by one, right? And so even if we have an u3, because u3 is perpendicular to each other, orthogonal to each other, orthogonal to u1 and u2, and so still the component or the linear combination coefficient with respect to u1 and u2, and these linear combination coefficient will not be dependent on u3, right? Okay, so that is another kind of intuitive understanding about why this theorem should be true, or why this relationship hold true. Okay. Okay, so in the case of a single line, so this is a kind of a special case where our subspace is spanned by only a single vector. Okay, only a single vector. So in case of having a single vector, so it is automatically just a orthogonal basis, because we only have a single vector. So we have no other vectors to satisfy the to satisfy the orthogonality of. Okay, right? So let's consider the subspace spanned by this U. Okay, and then their linear combination coefficient of linear combination will be represented as alpha times U, and then y is outside of the span or this line, and then this guy is orthogonal projection y hat, right? And then we do the same trick, y minus y hat, which is like this part. Okay, so this is our z, right? And z is perpendicular to u, right? And this guy is y minus alpha u, and this guy should be orthogonal to u, right? And so y, minus alpha u, and u should be equal to 0, and so y times u, and u dot u is our alpha, or linear combination coefficient, right? Okay, so this is a special case of having a one-dimensional subspace W. Okay, so that is called the orthogonal projection of y onto u, or the subspace spanned by u. Okay, and this C is called component of y orthogonal to u. Okay, so 그러니까 y를 그러니까 이게 성분을 분해를 한 거예요 지금. 이렇게 좀 직관적으로는 y라는 이 요소를 두 가지 요소를 분해를 한 것이고, 하나는 우리가 원래 갖고 있던 서브스페이스 성분으로, 그리고 또 하나는 그 성분에 있지 않은 또 다른 성분 두 개의 합으로 분해를 한 건데, 중요한 건 두 개의 분해를 할 때 이제 이 서브스페이스에 있지 않은 성분인 이 Z는, 이 Z가 우리의 서브스페이스와 항상 수직인 형태로 분해를 하겠다는 뜻이에요. 이거를 그러니까 분해를 이렇게 할 수도 있어요. 이렇게 하나 하고 이렇게 해도 y를 만들 수 있죠. 하나는 역시 서브스페이스 W에 있는 거, 하나는 있지 않은 거, 이 두 개 합으로 분해를 했는데, 이거 우리가 좀 약간 안 쳐준다 이거예요. 왜 저거 안 쳐주냐? 요 벡터, 요 Z라는 벡터가 올소고날 하지 않으니까 안 쳐주겠다 이거야. 우리가 항상 그래서 그 올소고날리티를 유지를 하는 형태로 분해를 해주겠다. Okay, so we are decomposing the original y into the two components, where the first one is belonging to our subspace and the second one is orthogonal to the given subspace. Okay, so that way the C is a component of y. Okay, but it is satisfying the orthogonality to the given subspace, or the basis vector u. Any questions so far? Okay, and then this is also written in this notation, orthogonal projection onto the line L. So this can be viewed as the subspace W, and this is the spanned by U, for example. And because it is spanned by a single vector, so that can be, so that way the subspace is just a line. So that way we just used an acronym of L, okay? Because L is a one-dimensional subspace, and the projection of this y, which is not necessarily inside of the subspace W or L. Okay, so in this case, it can be represented in this form. Okay, so in this example, we can easily compute their orthogonal projection. And then from this example, even though we verified it, even though we didn't verify it, but this is y hat, right? And then you can just compute it as a final three-dimensional vector. And then you can easily compute this z by just subtracting y hat from y. Okay, so you obtain y hat, and y is a 2, 3, 4, and then you just subtract between the two, and then you obtain z. And then you can easily verify that this z is orthogonal to 1, 2, 3, and 3, 3, negative 3. Okay, so you can further verify this kind of relationship, but we will just omit it because we already proved it in more general case. Okay, and then now let's study additional notion that slightly extends our orthogonal set. So we understand the definition of orthogonal set, but we also have another definition called orthonormal set. Okay, orthonormal set. So orthonormal set is orthogonal set, but we need to satisfy additional condition that each vector in our orthogonal set should be a unit vector, or each vector should have the length of 1. Okay, so when satisfying this additional constraint or condition, and then this set is not just called the orthogonal set, but it is called orthonormal set. Okay, so okay. So in this example, so 왜 이럴까요? 좀 닫으면 안 되겠네요. Okay, so I just created some orthogonal set. So can we make it as an orthonormal set? So we just simply normalize each vector, okay, so that their length becomes 1. And then after normalizing their vector lengths, and then are they still satisfying the orthogonality, being perpendicular to each other for any vector or any pair of vector? Yes, it is, right? Because the normalization so that the length becomes 1 will not change or affect any vector direction, right? So their vector angle will be just preserved. Okay, so that is the 뭐가 문제일까요? 이걸 닫아야 되나 말아야 되나? 자, 경건한 마음으로 한번. Okay, so that is an orthonormal set, and 오늘 수업은 여기까지 대신에 이 챕터는 여기까지. 다음 챕터로 넘어가죠. 뒤에 뭐 별거 없죠? 네. 뒤에 별거 없죠?
네.
So I'm currently using I was late, so I'm currently using my old equipment. So it may be due to this old equipment. So probably I'll cover the remaining part of the previous subchapter in the next class. But let's move to this chapter 6.3. Anyways, you guys know the orthonormal set, and also let me add just one explanation where so in the case of an R3, so that is one kind of a subspace, right? And then we can think of is the simplest possible form of orthonormal basis vector that are orthogonal to each other and having the length of 1. Okay, so what is that vector? So that vector is 1, 0, 0, and 0, 1, 0, and 0, 0, 1, right? And so if we compute the inner product between any pair between them, and then they have the 0 inner product value, right? And then let's suppose we choose maybe 372. I just chose any arbitrary three-dimensional vector, right? And then it is of course belonging to the R3, right? And then what about their linear combination coefficient, right? Although it's quite too simple problem, But yeah, if we just so yeah, one thing that we have to consider is, so if you remember the formula of obtaining this C1, so let's call this Y, and this is a U1, U2, and U3, and Y dot U1 and U1 dot U1, right? And so here, one additional convenience that we can have from having also normal set is this part is always 1, right? So simply, I mean, this C1 is further simplified as just a simple inner product between this Y and the U1, okay? So in this case, if we compute the inner product, and then the inner product will be 3, right? And 7 and 2. Okay, so yeah, we can compute this C1, C2, and C3 in this in this easy manner, right? And then now let's extend a little bit more about this orthogonal projection, but we already studied about it. Yeah, I think we don't have much to study additionally in this chapter, but yeah, it's a more kind of generalization to larger dimensional subspace. Okay, so here, so we are given a vector Y and also the subspace. Okay, and then so we can consider this a Y hat, which is an orthogonal projection of Y onto this subspace W. Okay, so here this theorem is saying this Y hat or orthogonal projection is a unique vector. Okay, so the orthogonal projection point cannot be like different point, but it is always represented as a unique point. And yeah, this is this Z part, which is an orthogonal component. Okay, and in this case, so we can imagine this U1 and maybe U2. Okay, and then we have Y hat over here, which is an orthogonal projection of Y. Okay, and in this case, this theorem is saying that this Y hat is, I mean, let's just consider some vector in our subspace W. Okay, this X will be represented as a linear combination of a U1 and U2, and it can be over here, over here, over here, right? It can be anywhere in our subspace. But yeah, let's try to choose the vector X that is closest possible to our Y. Okay, so in this case, so if we chose X over here, and then what is the distance between this X and Y? It will be like the vector length of this line segment, right? And in this case, we will have this vector length, right? And if we have to choose the vector X that has the minimum length or minimum distance to Y, and then it will be the orthogonal projection of Y onto the subspace W, which is Y hat. Okay, so Y, in other words, Y hat will work as the closest possible point in W from Y. Okay, so in that sense, this Y hat can be viewed as the best approximation of Y, where this Y hat can only be inside of subspace W. Okay, so that is kind of intuitive kind of meaning about this slide. Okay, so yeah, first of all, let's understand why this orthogonal projection is uniquely determined. Okay, so why is it uniquely determined? So yeah, we can formally prove it, but yeah, let's just intuitively understand it in this manner. So you guys know that yeah, when we are given the orthogonal basis of this W, and then given the y which is outside of W, and then its orthogonal projection. Okay, orthogonal projection is represented in this form, right? And u1 through up are just a fixed vector, right? They are just a fixed vector, and y is also a fixed vector, right? And here in this representation, all of them are fixed, and thus, yeah, given these fixed orthogonal basis vector and fixed y vector, and this y hat will be just uniquely defined, right? So it means there is no other orthogonal projection point. Okay, so yeah, so in terms of like a uniqueness of the solution. Okay, so when we considered it in the linear system, yeah, the solution can be sometimes a non-unique, or it can have a multiple different solutions. So similarly in here, in this case, the orthogonal projection, when it comes to their uniqueness, and the conclusion is this orthogonal projection is always unique. Okay, so that is the point. And this unique point of orthogonal projection works as the best approximation of the original point y. And in what sense? In what sense is it the best approximation? Yeah, it is because the length between the distance between the y and this the point inside of W can having a minimum length. Okay, so in that sense, we can view this y hat as a best approximation of y. Okay. So this is about the theorem and their kind of formal proof. But yeah, I'm gonna skip this part. Oh, but let me just show. So let me discuss why. Yeah, why the vector length, or the distance between y and y hat, is the minimum. Okay, so we can easily see or easily prove this has the minimum length as follows. Okay, so we have a y and y hat over here, and let's choose any other point from W. For example, suppose we have another vector x. Okay, in this case, we are just we are just comparing the lengths between the distance between the two. Okay, from the same y, which one or which length or which distance is shorter between the two. Okay, yeah, so y and y hat is shorter. And why is it so? It is because we can form this triangle. Okay, so this triangle, so this x and y hat are both inside of our W, right? So we chose two vectors from W, I mean inside of W, and then this guy, y hat minus x. This vector is also inside of W. And why is it so? Why is it so? Is it because y? I mean, so y is W and x is W. And this guy is also W. And why? Yeah, why is it so? I mean, it looks obvious from this figure, but yeah, we can also formally think of the formal reason why it should be true. And it is because the definition or the requirement of subspace. The subspace is what? Closed under linear combination, right? And this is a one special form of the linear combination of the two vectors chosen from the same subset or this subspace and so their linear combination is also inside of W. And then in this case, y minus y hat, this guy Z, is perpendicular to any vector from our subspace. And why is it so? This guy is anyways will be that guy will be represented as a linear combination of our orthonormal basis vectors, and by definition, this orthogonal component Z is perpendicular or orthogonal to each of our basis vector, right? And so it is orthogonal to any vector from W, right? And so we can guarantee that this angle over here is 90 degrees, right? And then so over here, let's call the vector length as a maybe A and B and maybe C. Okay, and then we can represent it as this Pythagorean theorem, right? So here, we are dealing with the real numbers. So from this, we can conclude that A is always less than or equal to C, right? So what is A and C? C is the line segment in this triangle that was formed by any other vector x, which is not, which is different from orthogonal projection, right? So if we form this triangle that has the 90 degree angle, and then from this Pythagorean theorem, and then this line segment is always smaller or equal to, smaller than or equal to another line segment C, and thus we can guarantee that the line segment formed by y hat to y, okay, so that length is the minimum possible one if we have to choose any vector from or any point from W. Okay, so in that sense, this length will become the minimum possible length. Any questions so far? Right, then let's look at this example. So we are given these two vectors. I think, we already discussed a kind of similar example in the previous slide where I just freely wrote some example where we have a 1, 2, 3 and 3, 3, negative 3, right? So let's check whether these basis vectors are orthogonal basis. Yes, it is, right? And so we have y, and then y hat can be obtained in this form, right? So this guy is this guy. Okay, and then y minus y hat, which is this guy, is our z, which is an orthogonal component of y, right? So this kind of decomposition of y as y hat and plus c, where y hat is inside of W, and what about z? Z is clearly not inside W, but furthermore, C is actually inside of W perpendicular, right? So that's how we kind of connect those things that we studied all together. So why is it so? You can easily understand it because this component Z is orthogonal to any vector from W. 되게 들어오고 싶었나 봐. Okay, so here, this kind of when considering this decomposition, y into y hat plus c, where y is completely inside of W. I mean, we are starting with the given subspace W, okay? But here, we can view this decomposition as, first component being inside of W, and the second component being completely like outside of W. And what's the meaning of being completely outside? So that is this guy, right? So perpendicular, it is belonging to the W perpendicular. Okay, so this is called orthogonal decomposition of W with respect to our subspace W. Orthogonal complement decomposition of Y with respect to the given subspace W. Okay, any questions so far? And here I want to discuss a little bit more about orthogonal complement. Okay, orthogonal complement. So you guys understood that given R5, and suppose W and its dimension is maybe 3, and what about W perpendicular? Its dimension will be 2, right? Sorry. Right? So in this case, we just we just choose 3 orthogonal bases over here, and we choose orthogonal basis from W perpendicular. Okay, so U1, U2, and U3, and maybe let's call it as a V1, V2 as the orthogonal basis of W perpendicular, still living in the R5. And then all together, collecting all 5 vectors, are they orthogonal set? Are they orthogonal set? So within each set, they are orthogonal set. But in order to have the orthogonal set for their union, in order for their union to be orthogonal set, we have to check these guys, right? All pairs across these 2 sets. Are these orthogonal? Yes, it is, because we choose any vector from W perpendicular, it should be orthogonal to any vector from W, right? And so from here, we have 5 number of orthogonal vector set, okay? And we understand that the orthogonal set is much more strict condition than linearly independent, and thus they are automatically linearly independent, right? And so we have 5 linearly independent vectors, right? And then these 5 vectors will work as the basis for R5. Okay, so once we collect the basis from W and W perpendicular and then add them together, and then they will work as the basis for our R5. Okay, so from here, suppose you have W as maybe 1-dimensional subspace, and then W perpendicular will be 4-dimensional subspace. And then Y can be just chosen from R5, for example. And then for any Y vector, this orthogonal decomposition will always exist, because W and W perpendicular, once adding them together, and then it will work as the basis for the entire subspace R5. So it means for any given vector in R5, it can be always represented as this form, where the decomposition is composed of these 2 vectors. So that way, this orthogonal decomposition will always exist, and also it is unique. So that is the kind of, high-level kind of point or the characteristic of this orthogonal decomposition. And so that's it for today. So let's continue this Wednesday.